So now we are going to discuss the concept of insertion in binary search tree. That means how we can insert a node into an existing binary search tree so that the properties of the binary search tree are not going to be hampered. Suppose consider this is a binary search tree, and if we want to insert a new node, suppose consider 75. So where to insert? So for inserting 75, so first consider this one. Compare 75 with the root 23. That means from here we should know whether 75 will be placed in the right subtree or in the left subtree. So if we compare 75 with 23, 75, that means the new node is larger, so it should be inserted in the right subtree. Now consider the right subtree. So here 44 is the root. So compare 44 with 75. So 75 is larger than 44. So 75 should be inserted in the right subtree of 44. So in the right subtree it has only one node and it is 52. So compare this 52 with 75. So 75 is greater than 52. That means it should be placed in the right subtree of this 52. So we can write like this. So 75 will be inserted here. That means 75 will become the right child of 52. So now consider we want to insert another node, that is suppose 40. So we want to insert another node and that is 40. So apply the same principle. So consider 23 and 40, compare 23 and 40. So 40 is larger than 23, so 40 should be inserted here in the right subtree. So now compare this 44 with 40. So 40 is smaller than the root here 44. So 40 should be placed here in the left part, or we should move to the left. Now we reach 35 and compare 35 with 40. So 40 is larger, so we should move here to the right. So here no right subtree is there, so we can insert 40 here. Now suppose we want to insert another node, that is 42. Suppose we want to insert 42. Now apply the same principle, compare with 23 and 40, compare 23, 42, 42 is larger, so move here. So 44, then 42, 42 is smaller, so move here. Then compare 35 and 42, 42 is larger, so move here. So 40 and 42, 42 is larger, so it should be inserted like this. Now suppose we want to insert another node, that is suppose consider 30 we want to insert. So now apply the same principle. So compare 30 with this 23. So 30 is larger, so move in this direction or move to the right subtree. Then here consider 44, compare 44 with 30, 30 is smaller, so move to the left or consider the left subtree. Now we find 35 or 35 with the new root for the left subtree. Then compare 35 with 30, 30 is smaller, so 30 must be inserted here. Now consider another node that we want to insert, that is 10. Suppose we want to insert 10. So apply the same principle, compare 23 and 10, 10 is smaller, so consider the left subtree. So In the left subtree 18 is the new root, so compare 18 with 10, 10 is smaller, so consider the left subtree. So here the new root is 12, so compare 12 with 10, so 10 is smaller, so just add 10 here. So in this way we can insert the new nodes to a binary search tree, so that the properties of binary search tree are going to be preserved. So we can consider another example here. Suppose we want to insert 7. We want to insert 7 in this binary search tree. So consider this 7 and the root here. So here root is 6 and we want to insert 7. So compare 7 is larger, so move to the right or consider the right subtree. So here in the right subtree 8 is the new root, then compare 8 and 7. So 7 is smaller, so 7 should be here in this left part. Similarly, you can insert any node to an existing binary search tree. So now consider the algorithm. So here the add BST, that means we are adding one node to an existing binary search tree. So the algorithm is add BST and it has two parameters, one is root and another one is the new node that we want to insert. And the precondition is that the root is address of the current node in a BST, new node is address of node containing data. So these are the explanation, what is the root and what is new node. So root is the address of current node in BST and new node is the address of node containing data. And what is the post or post condition? The new node is inserted into the tree and it is going to return the address of potential new tree root. So this is all about the algorithm, the explanation of algorithm, what is the precondition, what is the post condition and what the algorithm is going to return. Now consider the steps. So in step 1, if the tree is empty, so set root to new node and return new node. So if the tree is empty, just consider the new node as the root node and return that one. So this is end of if. Now in step 3, we want to find or locate the null subtree for insertion. That means where actually we want to insert. So find that one. So here. So if new node less than root, we can recursively consider the left subtree and new node. So if new node less than root, we can recursively call the method add BST by passing the left subtree and the new node. Else means if new node greater than root, call the add BST method recursively using the right subtree and new node, and end of if, end of the method. So it is a simple one like previously we have discussed. If the root value, like here you can consider, suppose you want to insert 7, so first compare this 6 or this root value with the new node 7. So if the root is smaller, then consider this one, this right subtree and 8 as the new root. So that part we are doing here only. So we are calling the same method and here right subtree. So previously it was root, now we are writing right subtree and new node. Now suppose consider one example like this. So assume some elements are given like 50, 75, 30, 60, then 35, then 10, then 90, then 21, then suppose 65, like this. So some elements are given and the question is draw a binary search tree for these elements. So for this you need to consider the elements following this order. So first we are reading 50. So as the new binary search tree is empty, so we want to make this 50 at the root node. Now the next element is 75. So 75 is greater than 50. So 75 here we are going to insert. Now 30. So 30 is less than 50. So always try to compare with the root node. The new element try to compare with the root node. So 30 compare with 50. So 30 is smaller. So 30 should be here. Now the next element is 60. So compare with 50. So 60 is larger. So come to the right. Now 75 compare with 60. 60 is smaller. So come to the left. So 60 is inserted here. Now read the next one, that is 35. So compare with 50. So 35 is smaller. So come to the left. So 30 compare with 35. 35 is larger. So come to the right. So 35 inserted here. Now read the next one, that is 10. So compare with the root 50. So 10 is smaller. So come to the left. So 30. 10 is smaller. Come to the left. No subtree is there. So add 10 here. Now read the next element, that is 90. So compare 90 with the root. So it is 50. 90 is larger. Come to the right. So it is 75. Compare 90. 90 is larger. Come to the right. So in the right no right subtree. So add 90 here. Now read the next one, that is 21. So compare again 21 with 50. 21 is smaller. Come to the left. So 30 and 21. 21 is smaller. Come to the left. Then 10 and 21. 21 is larger. Come to the right. So you can add 21 here. Now read the next element, that is 65. Follow the same approach. Compare 50 with 65. 65 is larger. Come to the right. So 75 and 65. 65 is smaller. Come to the left. Then 60 and 65. 65 is larger. So here we can insert 65. So if we want to draw the binary search tree following these elements, then the binary search tree will be like this. So now we are going to discuss about the deletion operation in a binary search tree. So if we want to remove one node from a binary search tree, or if we want to delete a node from a binary search tree, then there are three cases we need to consider. So the first one is, or we can say the case one is deleting a node that has no children, or we can say if we want to delete a leaf node, what is going to happen. So consider one example here. Suppose if we want to delete a node that has no children, or consider a leaf node, or for example if we want to delete 65. So here in this example we want to delete 65, that means this node. So remove the node from this binary search tree in such a way that the properties of the binary search tree are going to be preserved. So here you can observe 65 is the leaf node, or 65 do not have any children. So just simply remove 65 from the tree. So if we remove 65 directly, then the resulting binary search tree or the properties of the resulting binary search tree are preserved. So, we can directly remove a node that has no children. Like here we can consider another example. Suppose if you want to remove 55, so here this one. So 55 do not have any children. So simply remove 55 from this tree. So the case one is very simple. If we want to delete a node that has no children, so directly remove that from the node. So first find the node, so that is the obvious step. You need to search for that node, then find that, and after that just remove that one. So let us consider 55 was already there and 65 was also there. Okay. So now consider a node we want to delete that have one child. So here for one child, so let us consider this example. So here if we want to delete 60, suppose we want to delete 60, and here 60 has only one left child or one child, that is 55. So if we want to remove 60 from this, then make the parent of 55 to 70. That means here in this scenario the parent of 55 is 60, or let me write this one, the parent of 55 is 60 and we want to remove 60. So for that make parent of 55 to its grandparent. That means if this parent, if the parent is going to consider a real life scenario, like if some nodes or someone's parent expired or passed away due to some reason, then the grandparent is going to take care of the children. So similarly, if we want to remove 60 from here, so just make this 70 as the parent of 55. So this is also a simple one, no issues. Now consider one node that have only one right child. So here we are considering left child, so now consider right child. So for right child also the same situation. So here it is 60 and so assume it is 65. Now the parent of 65 is 60. Now if we want to remove 60, so 60 has one children, that is 65. So make this 65 or update its parent to 70. So now if just remove this one 60 and write here 65, the same thing. So just update the parent of the child and the parent becomes the grandparent, or the grandparent becomes the new parent. So it is a simple one. Now consider another scenario. So we have discussed deleting a node with one child. Now if we want to delete a node with two children, so consider we have one node, and if we want to delete a node that have two children, so let us consider it is 60 like our previous example, and it is 55 and it is 65. Okay. So now suppose we want to delete 70. So we want to delete this node 70. So you can consider 70 has two children. One is this one left subtree and another one is this one right subtree. So let me remove this part. Okay. So here you can observe, if you want to delete 70 that have two children, so we can find the maximum of the left subtree and replace that with the 70. Or another option is there, we can find the minimum of the right subtree and replace that with 70. So either or, you can find the, so the left subtree contains all the nodes that are smaller, all the values that are smaller than 70. So find the maximum among them and replace that with 70. Otherwise, another option we have, like this right subtree contains all the nodes that are greater than 70. So find the minimum here and replace that with 70. So let us consider the first one, that means find the maximum from this. So we have already discussed how to find maximum. So in this left subtree, if we want to find the maximum, so move to the extreme right. So here it is 60 root, move to the right, so it is 65. So now if we want to remove 70 from here, so if we want to remove 70 from here, so we can remove 70 from here, and here in the left subtree the maximum is 65. So copy this value of 65 to here and again delete 65 from here. So the new tree is like this. So I am drawing the tree once again. So after removing 70, the tree structure will be like this: 30, 10 and 40. So there is no change in the left part, and here 65 comes, and here 60 and 55, and it is 90. So after removing 70, the structure or the new binary search tree will be like this. Or we can follow another one, that is find the minimum from the right subtree. So that we are going to discuss. So just write 70 here, so like our original one, 70. Okay, so change the color to red, so it is 70, and we can remove this one also, so it is 65. This is the original tree, you can consider. Now if we want to remove this 70, so we can follow another approach, that is find the minimum from the right subtree. So here right subtree, it has only one node and the minimum is 90 and maximum is also 90 because it has only one node. So remove this 70 and replace this one with the minimum of the right subtree. That means remove 70 and copy the value of 90 to there. So if we follow, this is the first approach. So either you can follow the first approach or you can follow the second approach, no issues. Okay, so if we follow the second approach, so 50, then 30, then 90. So 50, then 30, then 90, then 30, the children are 10, 40, so it is 10, it is 40, then for 90 left 60, 55, 65, so it is 60, then 55, then 65, so like this. So this will be the new binary search tree after deleting 70 if we follow the second approach. That means if we replace the deleted node with the minimum of the right subtree. So, this will be the resultant binary search. So, either this one you can follow or this one. So, both are correct. So, both approaches are correct, and you need to follow only one approach. So, no need to follow both the approach, only one approach you can follow, because both are correct. In both the ways we can delete one node. Okay. So, now consider another example, or we can say the same example, and we want to delete another node. So, let it be 70 and it is 90. Okay. So, let me delete these things. Okay. So, now suppose we want to remove 50. Suppose we want to remove 50 from this binary search tree. Then we can replace this 50 with the minimum of the right subtree or the maximum of the left subtree. So, consider we want to find the maximum of the left subtree and replace that with 50. So, in the left subtree of 50 is like this: 30 is the root and 10 40. So, here what is the maximum? So, to find the maximum we have already discussed, move to the extreme left, move to the extreme right. So, here 30 is the root, move to the right 40. So, we cannot move here, move further. So, the node that is at the extreme right is 40. So, in the left subtree 40 is the maximum one. So, just replace this 50 with 40 and also delete 40 from its position. So, here you can observe. So, while we are performing the deletion operation of a node that have two children, then actually we are performing two deletion operations, or recursively we are also calling another one. So, that we will discuss later. Our objective is to delete 50. So, in the process of deleting 50, 40 is also deleted. So, we find the maximum here and we also remove 40 from this one. So, actually two deletion operations are performed. Okay. So, now just replace 50 with 40. So, the new tree will be like this: 40, then 30, then 10. So, this 40 previously this one is deleted. So, this is deleted from its original position. Then we are writing 70, 60, 90, 55 and 65. So, you can also find the minimum from the right one or right subtree and replace that with the root or with the node that we want to delete. So, that is, I am not discussing once again because we have already discussed. So, this one is the resulting binary search tree after deleting 50. Now, come to the algorithm part. So, we are writing the algorithm delete BST, the name of the algorithm, and we are passing two parameters, one is root, another one is the key that we want to delete. So, this algorithm deletes a node from BST. So, what is the precondition? Precondition is root is reference to node to be deleted and delete key is the key of node to be deleted, and the post is node is deleted that we want to delete, or the node that contains delete key is going to be deleted. And if delete key not found, root unchanged, and it returns true if not deleted and false if not deleted. So this is all about the algorithms. What is the precondition, what is the post condition, like this. Now if the tree is empty, return false, and this step 2 is and if. So if the tree is empty, we cannot delete the node. So this one is checking, the statement 1 2 is checking whether the tree is empty or not. Now we are checking if the key that we want to delete is less than root or greater than root. So if the delete key is less than root, then we are recursively moving to the left subtree. So here you can observe. So suppose we want to delete a node, suppose 10. So here in this example, if we want to delete a node 10, so the root is given here. So root this one. So now check whether root is greater than 10 or less than 10. So here you can observe, if you want to delete 10, so root value is 50. So 50 is greater than 10, then 10 must be in the left subtree. So now just update the value of root to here. So similarly we are doing the same thing. If delete key less than root, return delete key left subtree delete key. So we are just updating the root here, or we can say we are moving to the left subtree. And on the other hand, if delete key greater than root, then move to the right subtree. Now consider the same example here. Suppose this is the tree and this is the root given. So the root is 50 and assume we want to delete 60. So compare 60 with this one 50. So 60 is greater. So 60 must be in the right subtree. So for that, just update the value of root. So now the root becomes the right subtree or the root of the right subtree, or we are moving to this part only. Recursively we are coming to this part. So we are writing the same thing here. If delete key is greater than root, return delete BST right subtree delete key. Delete node found, test for leaf node. So we found the node and assume the node have no left subtree. Like this you can consider. So if this is the, so let me delete. Okay, so this is like the tree and no left subtree. That means root is like this, and let me delete this one. So no left subtree is there. So the root is given and here no left subtree. Then we can just update the root to here. So root is coming to here. So just update the root or return this one, this tree. If no left subtree is given, then return this part. That means directly we can remove this one 50. So the same thing is given. If no left subtree, make right subtree the root, return true. So if we want to delete this one, so no need. If we want to delete 50 here, so consider this once again. So the figure is like this. It is 70, it is 50, and root is referring to 50. So now if we want to remove 50 and 50 has only one child, so just update the value of root here. So if we update the root here, so 50 is automatically deleted. So the same thing we are writing. If no left subtree, make right subtree the root and return true. True means it is deleted. So else if on the other hand no right subtree. So if right subtree is not there, so consider this one. So assume the tree is like this. So it is 30 and it is 10, it is suppose 40 you can say. So it is 40 and no right subtree is there. So if no right subtree is there, so consider this one. So root is referring to 50 and we want to delete 50. So 50 has only one child. So just update this root or make this left subtree as root. So we can make this left subtree as root. So if we make this left subtree as root, then this 50 is automatically deleted. So this same thing we are writing here. If no right subtree, then make left subtree the root and return true. Now else part, this one, the node to be deleted, not a leaf, find largest node on left subtree. So if the node we want to delete, not a leaf node and that has both children, so find the largest node on the left subtree. So we know how to find the largest node in the left subtree and save the root in delete node. So we are saving the root in a variable delete node and set largest to largest BST left subtree. That means we are finding this largest one following this method. So largest BST left subtree we are passing and storing that in the variable largest, and delete node we are storing root. Now move data in the largest, that means the largest value in the left subtree is copied to the delete node. So initially delete node contains the root, now find the largest and copy the value of largest to delete node. Then again delete the largest we find from the left subtree. So for that we are writing return delete BST left subtree of delete node and key of largest. So first find the largest, copy the value of largest to the root, then delete the largest from the left subtree. So these are the steps that explains. So this is all about the algorithm for deletion. So now we are going to discuss about the time complexity or the time requirement for the operations that we have discussed in binary search tree. So first consider BST search. So to find whether one element is present in the list or not, we are applying this search operation or we are executing the search operation. So consider 75. So whether 75 is present in this binary search tree or not. So for that we compare 75 with this root node, then we follow one path from the root to the leaf node if the node is not present, or we can say in the worst case we follow one path from the root to a leaf depending on the condition whether it is larger or smaller. So for consider the example 75 here. So first compare with this one, then compare with this one, then compare with this one. So three comparisons required, or we are following the path like this, we are following this path and we can say this path is from the root to a leaf and this path is nothing but height. So the number of or the edge length here or the path from the root to leaf is nothing but the height of the tree. So the path from root to leaf is height, the path length we have already discussed. So the searching operation requires order of height, or we can say the searching operation have the time complexity that is equal to order of height. So in binary search tree the searching operation have the time complexity order of height. Now consider the insertion operation. So for insertion operation, first we need to find the place where we want to insert that node. So for finding, we need, or the time complexity is order of height, and once we find the position where we want to insert, just we update the reference values to refer to the root node. So that is a constant amount of time. So order of height plus constant is equal to order of height. So the insertion also takes order of height. Similarly for deletion also, the time complexity is order of height. So for searching one element is present in the list or not, it is order of height, and for insertion it is also order of height, and for deletion also it is order of height. And in generally or in average case, the height is log n. So the height of binary search tree is order of log n in the average case. So we can say the search operation, the insertion operation and the deletion operation of a binary search tree is order of log n, where n is the number of nodes. So log n is the average case. In the worst case, the height will be n. So consider the binary search tree like this. So here, if a binary search tree like 2, 5, 7, 9. So this is also a binary search tree, but here the height is n. Height is order of n, not log n. So in the worst case, the height is order of n in binary search tree, but in average case it is order of log n. So you can say the time complexity for searching, insertion and deletion is order of height, or we can say it is order of log n, because in average case the height is order of log n.